Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
So after seeing the constructional features, let's move on to the velocity triangle and the work done and the efficiencies of Francis turbine. So we'll see the velocity triangle for Francis turbine as we saw for Pelton wheel. In Pelton wheel, the triangle was different. Here in this case in Francis, it's a bit different because you know that the inlet is radial in Francis turbine and the outlet is axial. So the triangle looks something different here. So I'll draw the triangle, inlet and outlet triangle. So I've drawn the runner. So taking base of this runner, we'll draw both the triangles. So I've drawn the triangle. V1 is the inlet velocity, absolute velocity at inlet. VR1 is the relative velocity at inlet. U1 is the blade velocity at the inlet side. VR2 is the relative velocity at the outlet. V2 is the outlet velocity, absolute outlet velocity. U2 is the blade velocity at outlet. So after seeing the velocities, we'll see the angles now. So alpha is the inlet blade angle, or we can call it the guide vane angle, which is the angle made by the absolute velocity with the horizontal. Theta is the angle made by the relative velocity with the horizontal. Phi and beta. Here, as you can see here, since the velocity or at the outlet is axial, V2 has to be, the beta has to be 90 degree and V2 has to be drawn perpendicular. So this is how the triangle looks like for velocity. This is how the velocity triangle looks like for Francis turbine. The beta value is always 90 degree, in case of Francis turbine. Now comes the whirl velocity and the flow velocity. We all know that the whirl velocity is nothing but the component of the absolute velocity. Okay, let's do one thing. Let's consider each of the triangles separately and see. So whirl velocity and flow velocities are nothing but they are components of the absolute velocity at inlet. So the horizontal component of absolute velocity at inlet gives you the whirl velocity at the inlet, and the vertical component of the absolute velocity at inlet gives you the flow velocity at the inlet. Now let's see the same thing for the outlet velocity triangle. As you can see here, the absolute velocity at inlet was inclined, and in outlet triangle the absolute velocity at outlet is vertical. Since it is vertical, you cannot have components of it. So the horizontal component of the velocity at the outlet is 0. So it's a very important part of this Francis turbine. The whirl velocity at the outlet is 0, and the vertical component itself is the flow velocity. So V2 is not is VF2 and VW2 is 0. So this is a very important statement that I'm making here. In Francis turbine, the wall velocity at outlet is 0 since the flow is along the axis. There is no component, horizontal component along the of the V2. So wall velocity has to be 0. So that was all about this uh, diagram with the velocity triangles. Let's move on to the work done formulas for Francis turbine. So let's look at the work done by the jet on the Francis turbine. So before directly going on to the work done, let's go step by step. Let's look what is the force exerted by the jet on the impulse turbine. So the formula remains the same for the force exerted as we saw for Pelton wheel, as we saw in impact of jets. The force exerted by a jet of water onto a wheel is given by this. Is a very basic formula that we've already seen, that we've been saying throughout this subject. So the force exerted by the jet is rho a v1 vw1 plus vw2. So this is the force exerted by the jet of water onto the runner. Since here it is rotating, let's see what will be the torque. So once you know the force, you can get torque by multiplying it with radius. Since the radius is different at inlet and outlet, we'll be having R1 and R2. As it goes in, it becomes R1 and R2. Now, after getting torque from force, once you know torque, you can get work done. So the formula is, basic formula for work done is torque into omega. In angular motion, as in linear motion, we have work is force into distance. Similarly, in angular motion, we have work is T into omega. So we know the value of torque, we know the value of omega. Let's multiply and get the value of work done. Now R1 into omega is nothing but linear velocity. We all know that V is R omega, so R1 times omega gives linear velocity of the blade at the inlet, and R2 omega gives you the linear velocity of the blade at the outlet. So this is the formula for work done, and next we'll see what is efficiency, and once we know the work done, we can easily get the efficiency value. So we've got the value of work done, we saw what is force, after force we got torque. So we got the value of torque, and once you get torque, after you multiply torque with the angular velocity, you get work. Now this work done by the runner is known. Now we'll move on to getting efficiencies. So before moving on to efficiencies, let's do some manipulations in this formula. As I've already said earlier, the value of the whirl component at outlet for Francis turbine is 0. So let's eliminate it here only. So the Francis turbine VW2 is 0. We all know that. We have already seen that. So let's put 0 for that and see what the formula becomes. So the formula for work done per second is rho a v1 vw1 u1. Next is the hydraulic efficiency. Hydraulic efficiency is nothing, the same formula. Hydraulic efficiency is nothing but the power developed by the runner and divided by the power input to the runner. So the power developed by the runner is nothing but work done per second. Work done per second, we call it power. And the power output is nothing but, power developed is nothing but rho a v1 vw1 u1, and power input is nothing but rho gqh. You can cancel the like terms here. Rho is common. Rho times v1 is nothing but q. Q is rho I'm sorry, Q is A into V. So A into V is nothing but Q. So Q cancels out along with AV1. So you remain with so the hydraulic efficiency for Francis turbine is VW1 U1 upon GH. Is the mechanical efficiency. The same thing. Mechanical efficiency is nothing but the power output from the shaft divided by the power developed by the runner. That is the mechanical efficiency. And once you get the mechanical efficiency and the hydraulic efficiency, you can easily get the value of overall efficiency. So new overall is nothing but power output from the shaft to the power input to the runner. There's one more formula, that is a way in which you can relate both all three efficiencies. The overall efficiency is the product of hydraulic efficiency and the mechanical efficiency. So overall efficiency is hydraulic efficiency to mechanical efficiency. So any two you can get the third one. Next is we've seen the work done, we've seen efficiencies of the three. Next is the discharge for this particular turbine, Francis turbine. The value of discharge is the same formula. Q is A times velocity, but unlike the Pelton wheel where you had cross section area, here you don't have cross section. Here the flow enters through sides, through the circumference. So the value of area changes. The discharge for Francis turbine has a bit different formula. So as you can see, I've drawn a ring kind of a structure, and the discharge is not through the top, it is through sides. So discharge is from sides. So you should know the area of the side through which the water is getting in. And the width of the runner is known, the diameter is known. So the area through which the water gets in is nothing but circumference times the width. So pi d into b gives you the area through which the water gets in. Once you know the area, you know the velocity of the jet, you can get the discharge by multiplying it. So this is the formula for the discharge. So you cannot use the cross section area, since the water is not getting in through the cross section, it is getting in through sides. So you should know the area of the side through which the water gets in, and once I get the area and multiply it with velocity, I get the discharge. So this is how you calculate discharge in Francis turbine, and we already seen the formulas for hydraulic efficiency, mechanical efficiency, and the overall efficiency. So that was all about this topic. Next we'll see the numericals on this.